Okay, so we're just going to start with some basic double integrals in this new chapter on integration in multiple dimensions and all that. So just double and iterated integrals. And this is only over rectangles in this section. So in general, like, especially with this section, you're really just kind of doing sometimes, the basic setup is you have a region that's like rectangular region. Sometimes you have to set them up yourself, but it's very quick and easy, like just based off what your x and y values can take. But the first one is just some examples of them already set up. So 2xy dy dx, and then you have the limits 0 to 4 as your corresponds to dy, and x1s is 1 to 2. So seen here, you basically integrate with respect to y first. So you can think of it as 2x being like a constant, pulling it out. But I think this is the easiest thing to like sort of go over this section. It's like easier. The rest is where it starts getting a little more complicated, more thought-provoking what you have to do. Yeah, the works here though I think very detailed. I wrote these a little bit almost too detailed, but it's good when you're doing the first thing to go over this really in depth. This is an iterated integral. Of course, the process is just like is quite similar to normal integration, just that you have to do it twice kind of and with different variables each time. But yeah, because obviously the integral of y will be y squared over 2. Then when you use the limits y equals 4 and y equals 0, you get to, you eventually can simplify this down to 16x dx, and that becomes just, 16 times the integral. You can do it, so it's x squared over 2 and all that. But no, it's like you end up with 24 as your answer though. I don't think we need to overcomplicate this problem. Similar, show it off. Maybe a little bit less work this time, I don't know, just to make it clear. It's very easy because you just get the 16 thirds because there's no x in here, so 16 thirds x is just 16 thirds times x. You integrate it, and so it becomes quite quick. 16 is the answer. And then, oh yeah, this is one we have to start setting them up though for a few of these. So the region is 0 to 1 for x is between 0 and 1, and y is between 0 and 2. It's the rectangular region. It's given, and you give it in this setup. You just have to find the limits and then evaluate it. So it's obviously going to be so we can do this as dy dx. With rectangular region in particular, it's very easy. You can technically do this with respect to y and x or with respect to x and y. The order you just have to make sure your limits correspond to this. And you can do that quite a lot, just have different limit orders, but like in this one specifically, it's very easy to switch between. You don't have to do any specific thought-provoking things, exercises or anything. Because eventually you're going to have to start graphing these out a little bit to see what's going on. This one you don't. But no, I basically set it up so we integrate with respect to y first and x, but you could do it x and then y if you really want to. So that's why it's 1, 0, 2, 0, because the innermost is y related, so it's 0 to 2, and then 0 to 1 is to x. You have to follow this order. You integrate the first one and the innermost one, and then the outermost dy in this, and then add in dx out of the outermost. I mean, you can just follow the process. I think I've made it quite detailed. 16 minus 4x is what this integral, the first one, becomes after all this work. Then we just have to integrate that. So 16 minus 4x, with respect to integrating that, you get 16x minus 4x squared over 2, and then x equals 1, x equals 0, your limits. You eventually get 14 as the answer to that problem. And now we do another one. We have the region, and I was kind of a fool here, and I tried to integrate with respect to y first, and I just think we'd have to do integration by parts. I mean, we're gonna have to do that a few times of it throughout the course of these things, but like not this time. We can avoid it. For now, let's avoid integration by parts. I think you'd have to for this if you do dy dx. Now let's do it with respect to x first. I mean, it's a good time to bring up that point. So I do it. So pi and 0 is y, and negative 1 to 1 is x. So we have negative 1 to 1 is and 0 to pi. So if you do this with respect to x, you basically get, well, y cosine y will be like a constant. I can try to. So it's like x squared over 2. And that's, was 1 and 0. I mean 1 and negative 1, so you get 1 squared over 2 minus negative 1 squared over 2. You get 1 over 1 half minus 1 half, which equals 0 eventually, so times y cosine y, so it equals 0. And you can't really integrate from there. The integral of 0 will be 0. Because it's like a constant, so you pull it out, it'd be equal to x times 0, basically, whatever. So technically pi times 0 would be 0 in this case. So it doesn't, yeah, when you get a 0, that means your integral of 0 is going to be 0 no matter what. Pretty much. That's an interesting part, but now it's time for this one. So 0 less than or equal to x less than or equal to ln 2, and 0 less than or equal to y less than or equal to ln 2. And it's e to the x minus y. So, of course, we put in dy dx for dA like usual values. So we're going to do y first. Maybe x would be easier, I don't know, but like I just did y. So this is e to the x. Oh yeah, right, I do it down here in brown first to eventually get there. Because integrating e to the x and n will be very easy here, but you'll see. So the brown shows the process of integrating the first integral with respect to y, which I try to show in a different color to emphasize the difference. I tried to separate, I mean, just especially for these ones as an introduction, you really do sometimes need to do that. Like, try to think of doing it one at a time, the integrals, definitely. You always have to, this way it kind of emphasizes that. Yeah, so the process goes through all that. Because e to the x divided by e to the y is what e to the x minus y is, basically, is where it comes from, the idea of the property. You can also write that as e to the x times e to the negative y. But we're integrating with respect to y, so e to the x can be dropped out. And that makes it very, very possible to do an integration. Then you just go through all the processes. Because e to the negative y will be like e to the u, where u equals negative y, if you really wanted to be technical. You don't really have to show that. The point is that it's, e to the u divided by du, and du would be negative 1 and all that. So it's negative e to the negative y, because dividing by negative 1 gives you the negative just of that. But eventually e to the x over 2 is given as its answer, and so 1 half time, you basically can take out the 2 and get 1 half times the integral 0 to ln 2 of e to the x dx. And that's just equal to e to the x, so it's 1 half times e to the x, and then you just integrate, you put in the limits. And it becomes eventually 1 half the answer. Right there. Okay. So this one, so 0 to 1, 0 to 2 for its x and y. And it's x y cubed over x squared plus 1 dA. So I decided to do it with respect to x, because that way y cubed won't matter. But then you have to do x. We have this x squared plus 1 and x, so it's like x over x squared plus 1 basically is what we're worried about here. So you can write this as u equals x squared plus 1, that means dx equals du over 2x, because du equals 2x dx. So when you basically you can get rid of the x, so it's just in terms of u basically what you need to integrate. Comes y cubed over 2 times the integral of 1 over u du. You get a natural log answer. That's what it is. And I also set down u equals 1 squared, u equals 0 squared for your components to get 2 and 1, plus 1, because that's u equals x squared plus 1. So it's u is 1 and 2, not 0 and 1. But eventually you get y cubed over 2 times ln 2. This is indicating brown. And in the end you have to integrate y cubed now, which is just by itself. So y cubed become, those, because ln 2 divided by 2 is a constant. So y to the 4th over 4 is what that becomes, integrand. And you solve it, and you get 2 ln 2. Find the volume of the region bounded above. Okay, so a couple word problems, just because I think especially for this one, it's good to look at some. There's always a couple word problems. These aren't particularly hard. Find the volume of the region bounded above by the paraboloid z equals x squared plus y squared, and below by the square. That's like your region, yeah, by the square, it's bounded. So, it's the general formula for volume of this specific type, and then you have your the z equals x squared plus y squared will be what you integrate. Then you have your limits, -1 to 1 for both of them, basically. And let's do it. It really won't change, I don't think, because it's x squared plus y squared. You integrate either way, it's going to be the same result easily. Almost the exact same steps, pretty much. But you can go through the process here. I did dx dy. It's one of those where it's like basically the same. It's pretty much going to be the same amount of work, regardless of which direction you integrate by. And you get 8/3, and I say cube units or whatever, because it's technically a volume. I mean, it's kind of hard to explain this stuff besides like what's written down, like this one in specific, because it's really mostly computations. This is like spoon feeding. This stuff is like given in the problem. Like if you ever had a pure rectangular coordinates, there's not much you need to know. Be able to set it up. Find the volume of the region bounded above by the plane. Z equals 2 minus x minus y. Yeah, it's above and below by the square. Yeah. So v equals, it's a double integral. Very similar to the last one, and the order probably won't change the difficulty of this either. And you go through the process, eventually get one cube unit. And that's that. I mean, I don't think this needs much explanation. You really just follow the steps, and there's not much. You don't have to draw out anything of the kind or anything.